All right, this is AP, AB, and BC Calculus. We're doing Unit 3, Section 4, which is differentiating inverse trigonometric functions. All right, so we're going to go ahead and learn 6 more of the differentiation rules today. But if you'll notice that you can figure out the co-functions, the stuff that I wrote in red, if you memorize the blue ones. So although it's technically 6 different rules, I think you're going to find that you can memorize these sort of as 3 rules with a little bit of a caveat. So a couple notation things. I don't care if you use arc sine or inverse sine, but you should know that they are both the same thing and that they are interchangeable. The same thing with arc tan and inverse tan, arc secant and inverse secant, arc cosine and inverse cosine, arc cotangent and inverse cotangent, and arc cosecant and inverse cosecant. So let's look at how these rules work. So if you're differentiating the arc sine of x, you're going to get 1 over the square root of 1 minus x squared. Notice that that's sine. If you were to do cosine, it's exactly the same pattern with a negative in front. So negative 1 over, and then in the square root, 1 minus x squared. If you differentiate arctangent, you get 1 over x squared plus 1. Notice it's the one that does not have a root because the other 2 rules do. And if you do cotangent, which would be, so arc cotangent instead of arctangent, is going to be the exact same rule, that 1 over x squared plus 1, but with a negative, right? And then if you differentiate arc secant, it's going to be a 1 over the absolute value of 1, and then in the square root, the x squared is in the front seat, so it's x squared minus 1. Notice the difference there. In the arc sine, it's a 1 minus x squared in the root. In the arc secant, it's an x squared minus 1. Notice that cosecant is the same formula, but with a negative. So I would suggest that you make note cards for these, right? I wouldn't suggest that you necessarily make, like I would pick either arc sine or inverse sine to make the front of your note card. It really doesn't matter to me. So like I wouldn't put both of these because they mean the same thing. And then the back of your note card would be the differentiation pattern, okay? So please make note cards. You had about 14 to 16 before, so these 6 pretty much push you up to that 2 dozen that I was talking about. So again, we're going to have about 2 dozen rules, and you pretty much know almost all of them at this point for differentiation. So, all right, let's go ahead and differentiate. So we're going to differentiate with respect to x. Arc sine of this quantity 2x squared. Okay, so when we differentiate, switching colors for a sec. Okay, when we differentiate arc sine, right, the pattern is 1 over the square root of 1 minus, and then it's whatever's inside the arc sine squared. So it's going to be a 2x squared quantity squared. But then we need to do the chain rule, right, because there's a thing inside arc sine that's not just an x. So I'm going to differentiate that and make it a 4x. So what's going to happen is I'm going to get that this is a 4x on top of the square root of 1 minus a 4x to the 4th. And that's my answer, okay? Same thing with this arc cotangent, right? There's a function inside my function. This is an x to the 1/2. So when I differentiate arc cotangent, it's a cotangent, so it's going to have a negative. So it's a negative 1 over whatever was inside the cotangent square, or the arc cotangent squared, plus 1. But I then have to differentiate. I have to do the chain rule because the stuff inside has its own derivative, and it's going to look like this. So what's going to happen is I'm going to get a negative 1, and then what you'll see here, right, this is going to be a regular x plus 1, right, because that's what root x squared would be. And then this is going to be a 2 root x on the bottom. So you're going to get something that looks kind of like this, and you could clean it up and make it look different, but it's going to look something like this, right? And then when I differentiate the inverse secant of e to the x, right, notice that there is a function inside my function. So differentiating the inverse secant is 1 over the absolute value of what's inside the arc secant, right, and then the square root of that thing squared minus 1. But then I have to do the chain rule and differentiate e to the x, which will be another e to the x. Now, normally I would tell you that an e to the x and an absolute, like a something and the absolute value of that something don't cancel. But remember that there's a trick that e to the x is always a positive number, right? If you have a positive base, like e is a little bit smaller than 3, if you have a positive number to a power, it's always positive. So because of that, I don't actually need these absolute values. And what this looks like is an e to the x on top of an e to the x times this square root. Well, these guys can cancel, and I can just make that a 1. So my answer is going to look like this. And again, that's a special thing because e to the x is positive. All right, let me give you a P1 to try. Go ahead and differentiate. Again, notice that when you have a co-function like cosine or cosecant, you're going to end up with a negative there, right? So pause me if you want. So when I differentiate arc cosine, I'm going to get a negative 1 over the square root of 1 minus whatever's inside my arc cosine squared, right? And then I'm going to times by the derivative of this. It's kind of worth memorizing that this is the derivative of the square root of x, right? It's a 1/2 x to the negative 1/2, but it's going to happen a lot, so you might as well get used to it. This is a negative 1 over, I'm going to go ahead and write this as a 2 root x times this root, and you can clean it up if you want, but I'm okay with that. That seems fine by me. All right, when I differentiate tangent, right, arctangent rather, I'm going to get 1 over this thing squared, so e to the x quantity squared plus 1, and then I have to do the chain rule, so times the derivative of the stuff that was inside. So I'm going to get an e to the x over an e to the 2x plus 1. When I differentiate arc cosecant, remember that co means it's going to have a negative, right? So I'm going to get a negative 1 on top of the absolute value of 5x cubed, right, times the square root of 5x cubed quantity squared minus 1, and then I need to do my chain rule, which is going to give me a 15x squared for the top, right? Now, I can't cancel anything out because I don't know about x's. I could actually cancel a 5 out if I wanted. So this is a negative 15x squared over the absolute value of 5x cubed, and then in the square root, I'm going to get a 25x to the 6th minus 1. Now, this answer is fine. You can factor the 5 out of the absolute value because it's a positive 5. So if you wanted, you might see this answer as a negative 3x squared over the absolute value of x cubed, square root of 25x to the 6th minus 1. That, you might see that too. Or a similar variation. Remember, you don't have to have every possible answer. You just have to be able to look at answers that are presented to you and take a deep breath and see if one of them matches your answer. So we've seen this question before. We're going to write the equation of the line that is tangent and normal to the curve at the given x value. Again, we keep seeing this question because the goal is to be able to do this same relatively simple question as the difficulty of the other parts of the problem escalate. So we know anytime we see the equation of a line, we're going to need two things, right? Forever and always, we're going to need a point, right? We'll find that first because that's mostly a pre-calc skill. So it's going to be 1/4 comma blank, and we're going to find that blank by plugging in here. So my point is going to be f of 1/4, which is going to be the inverse sine of 2 times 1/4 would be 1/2. So this is basically saying sine of some mystery angle gives you 1/2. What is it? Well, the output of an inverse sine, like any inverse sine ever, starts at negative pi over 2 and goes up to pi over 2, so that it hits every possible y value because sine is the y value in the unit circle. The only y value in that window that has a value of 1/2 is at pi over 6. So this is going to be a pi over 6, okay? So pi over 6. All right, so that's our point. The second thing we're going to need is a slope, right? So that's the first half. That's the half that's not technically calc, although it does definitely use your pre-calc skills. The second thing I'm going to need is the slope, right? And I know that my slope for A is going to be f prime evaluated at 1/4, right? That's my tangent slope. And that my slope for B, my normal slope, is going to be the opposite reciprocal of that answer, right? So opposite reciprocal of MT, right? So my job now is going to be to find f prime of 1/4 and then go from there. So let's find f prime. So f prime of x, when I differentiate an arc sine, I'm going to get 1 over the square root of 1 minus whatever stuff is in the arc sine squared. So that's going to be a 2x quantity squared, which is going to be a 4x squared, right? Times, and then because there's something inside the arc sine, I need to do the chain rule, and the derivative of 2x is 2. So I'm going to get that this is a 2 over the square root of 1 minus a 4x squared. Great. So now I need f prime of 1/4. Well, that's going to be a 2 on top of the square root of 1 minus. So this is going to be a 4 times a 1/16, right? 4 times 1/16 is 4/16 or 1/4. So I get that this is a 2 over the square root of 3/4, right? Because that's what 4/4 minus 1/4 would be, which is the same as a 2 over, this is a root 3 over 2, right? Because it'd be root 3 over root 4. So I'm going to get that my f prime of 1/4 is a 2 times the reciprocal of that denominator. I get a 4 over root 3. And that answer is great. I would not rationalize that answer. It's okay if you want to call it a 4 root 3 over 3, but it's not a great idea. Why make your life harder? So my tangent slope is a 4 over a root 3, which means that my normal slope is a negative root 3 over 4. And then I can write my two answers. So y minus the y value equals 4 over root 3, that's my m, x minus the 1/4, that's my tangent line. And my normal line is exactly the same answer but with a negative root 3 over 4 in its place. Okay? And those are my two answers. Again, if you wanted to add the pi over 6 to the other side in both cases to solve for y, that would be the easiest way to solve for y. All right, let's try another one. All right, write the equation of the line tangent and normal to the curve, and here's your value. So you can go ahead and pause me if you want. Again, the first thing I'm going to advocate that you do is the thing that is not calculus. So you need the point 2 comma blank. To find that blank, you need f of 2, which is going to be the inverse tangent of 1. Well, tangent has the same output window as sine, arctangent rather, has the same output window as sine, except it has open circles at the y-axis because that would be a vertical asymptote. So I need somewhere in this window where the tangent, so remember that tangent of theta is the y on the unit circle on top of the x on the unit circle. So if tangent is 1, what that's telling you is the y on the unit circle and the x on the unit circle have to have the same value, and that happens at pi over 4. So at all the pi over 4s, both tangent and cotangent are 1 or negative 1, and it just depends on which quadrant you're in. So I now have my point. The second thing I'm going to need is I'm going to need a slope, right? And I know that my tangent slope is going to be f prime evaluated at 2, and that my normal slope is going to be the opposite reciprocal of that value, right? I just have to find that value. So let's go ahead and find our f prime. So if it's easier for you to think of this as a 1/2 x, that's fine. Like inside the inverse tangent, if it's easier to think of it as a 1/2 coefficient in front of the x, that's great. It's up to you. So my f prime of x is going to be 1 over the stuff inside the arctangent squared plus a 1, and then I have to differentiate the inside of the arctan, which would just be a 1/2. So it's up to you how much you want to clean this up before you start. It really is. I don't care. Because I'm going to argue that it's maybe easier to find f prime of, not 1, f prime of 2 by just plugging in now. That's going to be a 1 over a 1 squared plus 1 all times a 1/2. So that's a 1/2 times a 1/2, which is a 4th. And I think that was easier than trying to clean that up first. Once I know that that's my tangent slope, I know that my normal slope must be a negative 4, and now I can answer both questions. Y minus my y value equals m, which is a 1/4 in the case of the tangent line, x minus the 2. And for my normal line, it's the exact same setup, but I'm going to use a negative 4 as my slope. And again, if you want to add the pi over 4s to the other side to solve both of those for y, you absolutely could, but you really... All right, so for E3, you probably are looking at this thinking, oh my gosh, Hogan, what are you doing? I felt okay at E2, and now I'm having a heart attack. I don't know what this is. So the left-hand side of this looks disgusting. There are essentially no numbers except for the 0 on the left-hand side of this, right? There's A's and there's H's and there's C's and O's and S's, and it's just kind of miserable. And aside from the 0 and the negative 1 exponents, you've got no numbers, and you're probably having a mild panic attack. Take a deep breath. It's going to be okay. When you see something that looks like this, the first thing you should do is stop and think, do I recognize a pattern here that I've seen before? And hopefully you do. Hopefully you remember that this is essentially the pattern for f prime of a, where your f of x function is this thing, right? So f of x being cosine inverse of x, right? That's because remember we've seen this formula that f prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h, right? And that's absolutely what this is, but instead of x's, we see that their a is plugged in here, right? And instead of just a generic f of something, we see that we have a function, right? So the reason I mention this is because this is where you're most likely to see this kind of limit definition of the derivative that we did early on. You're going to see it in a problem where the pattern recognition is the most important. So really what we're being asked is f prime of a equals negative 4, help me find a. Well, if I recognize that f of x is inverse cosine, then I can find f prime of x using my knowledge of the differentiation rules, right? It's going to be a negative 1 on top of the square root of 1 minus x squared. Great. Well, that means that f prime of a, which is the number I'm trying to find, is a negative 1 over the square root of 1 minus a squared. Great. So negative 1 over the square root of 1 minus a squared is apparently a negative 4. I'm going to go ahead and solve for a. When I multiply the root over, I get negative 1 equals negative 4 square root of 1 minus a squared. I'll divide by the negative 4, and I get 1/4 equals the square root of 1 minus a squared. To get rid of the square root, I'm going to square both sides. So I'm going to get 1/4 quantity squared equals 1 minus a squared, right? So 1/4 squared is going to be 1/16 equals 1 minus a squared. Subtract the 1 over. So remember, a 1 is actually 16/16. So when I subtract that over, I get negative 15/16 equals negative a squared. So 15/16 is my a squared, which means a must be plus or minus the square root of 15/16, which is not a wrong answer, but I think you're more likely to see it as a plus or minus root 15 all over a 4, right? Because the root 16 would be a 4. So that's the idea. It's all about the pattern recognition. Even if you recognize the pattern, it's still not a short problem, but the problem turns into mostly algebra if you can recognize the pattern. All right, let's go ahead and try a P3. All right, same idea. You're recognizing a pattern. So take a minute, try it, pause me. Cool, you're back. Let's do this. So this is the formula for f prime of a, where my f is this function, right? So it's a formula where my f of x is the inverse tangent of x, and I want to find f prime of a. So f prime of x should be 1 over x squared plus 1, right? That should be the derivative of this function, which means my f prime of a should be a 1 over a squared plus 1, right? So now that I know that, I'm trying to find when that is equal to 1/10. So 1 over a squared plus 1 equals 1/10. I'm going to cross multiply because this is a proportion, right? So I'm going to get a squared plus 1 equals a 10. A squared is a 9, so my a should be a plus or minus 3. Cool. All right. For E4, we're going to write the equation of the line that is tangential and normal to the curve at the given point. Tangential is the adjectival form of the word tangent. Okay, so cool. In order to write the equation of a line, I need two things, right? Number one, I need a point, right? I know that the point is going to be root 3 over 8 comma some mystery value, right? So in order to find that mystery value, I'm going to do f of root 3 over 8, which is going to be the arc sine or the inverse sine of a root 3 over 2, right? Because the 4 and 8 would cancel. So the question is, where in this window from here to here is the sine value a root 3 over 2? And the answer is at pi over 3. Again, knowing your unit circle is going to matter. The second thing I need is a slope, right? I know that my tangent slope is going to be f prime of root 3 over 8. And I know that my normal slope, so that was a, and that my normal slope is going to be the opposite reciprocal of that value. So let's go ahead and find my f prime. So f prime should be 1 over the square root of 1 minus whatever's inside the arc sine, which in this case is a 4x quantity squared. So that's going to be a 16x squared. And then I'm going to times by the derivative of the 4x. So that means that my f prime of root 3 over 8 should be a 1 over, and then in the square root, this is going to be a 1 minus. So this is going to be a 16. When you square the root 3, you get a 3, right? And when you square the 8, you're going to get a 64, right? And then there's a 4 on top. I was going to put times 4 out here, but it makes more sense to just go ahead and put the 4 up top. So I'm going to cancel the 16 and the 64 to get a 4, because that's going to make my life a lot easier. So I get a 4 on top of a square root of 1 minus 3/4, right? Well, that's a 4 on top of a square root of, that's 4/4 minus 3/4, which is 1/4. So it's a 4 on top of a 1/2, which means that the tangent slope is an 8. Once I know tangent slope is an 8, my normal slope is a negative 1/8, and I can write my two answers. So A, y minus the pi over 3 equals my 8 times the quantity x minus root 3 over 8. And for B, I'm going to write the same exact answer, but instead of the 8, I'm going to use a negative 1/8. Okay? All right, we'll go ahead and try a P4. Same idea. All right, so you have arctan of 2x, and we're using negative 1/2. Cool. So first thing I need is a point. Right? I know it's negative 1/2 comma blank, and the way I find that blank is by doing f of negative 1/2, which is going to be the arctan of negative 1. So that's asking you tangent of theta equals negative 1 somewhere. Well, we already discussed that tangents are 1s and negative 1s at the pi over 4s. Since this is the output of arctan, this is the winner, and the answer is negative pi over 4. Notice that that's not 7 pi over 4. because the window starts here and goes to here. 7 pi over 4 would be a whole nother lap around. So I get negative pi over 4. The second thing I'm going to need is a slope, right? I know that my slope for A, my tangent slope, is going to be f prime of negative 1/2. And I know that my slope for B, the normal slope, is going to be the opposite reciprocal of that value, right? And realistically, on an AP test, you're probably not going to be asked to find both tangent and normal, but the best way to prep for it is to make sure we know how to find both all the time. So let's go ahead and find our f prime. So the derivative of arctan is 1 over whatever's inside the arctan squared plus 1, and then we have to differentiate the thing inside the arctan. So we're going to get a 2 over a 4x squared plus 1. So that means that f prime of negative 1/2 is a 2 over, well, this is going to be a 4 times a 1/4 plus 1, right? Because negative 1/2 squared is a 1/4. So I'm going to get that this is a 2 over a 2, which is just a 1, right? Once I know that, my tangent slope is a 1. That means my normal slope is technically, if you flip it, you still get a 1, and then the opposite part is a negative 1. So my answer to A is y minus my y value, which is going to end up being a plus pi over 4 or minus a negative pi over 4, equals 1 in parentheses x minus a negative 1/2 or x plus a 1/2. And my answer to B is going to be exactly the same answer. Sorry, that's a plus pi over 4 with a negative 1 as my slope. And that's my answer. All right. I believe we have one more practice problem and one more example. Okay, so we're going to evaluate the limit. So we're evaluating the limit as x approaches 2 of f of x minus f of 2 minus or over x minus 2 for inverse secant. So this is another one where we're doing pattern recognition. So I want you to recall that f prime of A is the limit as x approaches A of f of x minus f of A over x minus A. The reason I mention that is because what this is asking you for is that this is asking you for f prime of 2. That's 100% what this is asking for. So you're not going to use the limit. You're going to use your knowledge of how to find the derivative. So f prime of x for a secant should be 1 over the absolute value of the secant and then the square root of this x squared minus a 1, right? The stuff inside the secant, the arc secant rather. So that's my f prime of x. If I want f prime of 2, that's going to be a 1 over, absolute value of 2 is just a 2, and in the square root, I'm going to get a 4 minus 1. So I get a 1 over 2 root 3, and that's it, right? So again, this is about pattern recognition. It's not to say that there isn't work, but most of the work is recognizing the pattern that you've memorized and then applying the skill of knowing what point you're plugging in. All right, so last one, P5, same idea. Again, remember that you've seen this pattern before. So this is a pattern, right? We want to recognize that this is the f prime of A, right? Because it's the limit as x approaches A, right? We see that. Here my A is a negative root 2 over 2 of f of x minus f of A over x minus A. And this is the kind of tricky question the AP likes to ask. So this is asking you for f prime of negative root 2 over 2. That's my A in this situation. So I go ahead and find f prime of x. Well, the derivative of inverse cosine is a negative 1 over the square root of 1 minus x squared. So that means my f prime of negative root 2 over 2 is going to be a negative 1 over the square root of 1 minus this negative root 2 over 2 quantity squared. So then we need to clean up a little bit because, of course, they're not going to leave the answer looking like this. It's a negative 1 on top of the square root of 1 minus. So when you square a root 2, you just get a 2. When you square the 2 on the bottom, you get a 4. So I'm going to end up getting this is a negative 1 over the square root of 1/2. They're probably not going to leave it like that either. So it's probably going to be a negative 1 on top of a 1 over root 2, right? Because it would be root 1 over root 2, which is the same as a negative 1 times a root 2 over 1, which means that you're going to end up with an answer that is a negative root 2, okay? And that's the gist of it. Notice that this uses a lot of skills we've seen before. It uses knowing what the limit definitions of the derivative could be. It uses a lot of the unit circle, right? So when you see arc trig, kind of keep in your brain that unit circle is going to come up.